So the law of conservation, of energy, it's fundamental to our universe. It says this: the total energy of a closed system, and by closed system I mean one that doesn't have any outside sources of energy. You're not adding gunpowder if it's a chemical reaction. You're not adding fuel if it's a motor. It's a closed system, is neither increased nor decreased through any process. Energy can be transformed from one form to another, but the total remains constant. A poetic way of saying this, Stephen, is the total amount of energy in the universe has never changed since the Big Bang. The amount of energy in the universe is constant. You can change it from one type to another. In fact, there's a related concept called entropy in the second law of thermodynamics, which also suggests that most energy is gradually going to turn into cold, unusable heat. The end of the universe will end up with the universe being an average temperature of about 3 or 4 degrees above absolute zero, and nothing will work anymore. Preview of coming attractions. I wrote here, Mr. Dewick has a good demo for this. I do. Here's our proof. According to the work energy theorem, if we have a closed system with no outside sources of energy, we get no useful work. What is the work energy theorem? It's from your blue sheet. It's not force times distance. It's that third definition of work that had energies in it. Which one was that, Patrick?
Changing potential energy plus changing kinetic energy.
Now we're going to let the amount of work be zero because it's a closed system, which means you get nothing useful. The universe is a closed system. Energy does not enter the universe from outside of the universe. What's changing anything? So I'm going to write this as 0 equals PE final minus PE initial plus KE final minus KE initial. And then, Tato, the two negative terms, the negative PEI and the negative KEI, I'm just going to plus them over to the zero side. And this gives us the law of conservation of energy. It says the amount of kinetic that you start with and the amount of potential that you start with. If you add up those two types of energy, the amount of kinetic that you finish with has to equal the amount of potential that you finish with. And that's on your formula sheet. Well, this is in our magic physics world where everything works nice. In real life, you tend to lose some energy to sound and heat and dissipative other types of energy. We lump that all into heat. So if we want to include friction, we would actually get this. KE initial. Oh, come here. Oh, my pen's acting up again. Why does it suddenly do that? Pause. Let's try that again. So if we include friction, we're going to have KE initial plus PE initial equals KE final plus PE final plus heat. And the beauty of this also is the fact that because work and energy are scalars, this allows us to analyze or look at or deal with yucky curvy paths. Like skateboarding. Put your pencils down and look up. So here is our energy skate park. And if I start out our skater, what I've just done is I've given him potential energy. You can see it in the blue graph, the blue bar graph. Oh. I need to zoom down a tiny, there we go. So there's the total amount of energy, and I know it's small. Unfortunately, on my new machine, it's small. That yellow bar there is how much energy there is in total. What do you notice about that yellow bar there? It is, I'm looking for a word that begins with the letter C. It's constant. That's the law of conservation of energy. Now, at the top, for a split second, what's my speed? What's my kinetic energy right here, this green bar? All of my energy has turned into gravitational potential. At the bottom, I have my maximum kinetic. I have some potential because am I on the ground? Here's one of the lovely things about work and energy. Because it's a scalar, I can put the ground wherever I want. So what I'm actually going to do is I'm going to put the ground, I'll let 0 be right there. Why not? And now I have a lovely situation where all of my potential is being turned into kinetic, and at the top, all of my kinetic is being turned into potential. This is the law of conservation of energy. Now, this is not realistic, Zach. In real life, on a skate ramp, you can't just go back and forth, back and forth, back and forth. In real life, if you want to go back and forth, either you have to add energy from your body, or if you don't add energy, you'll gradually slow down and come to a stop. So we can turn friction on. Right here, you can't see very well from the back row, but it does say coefficient of friction. I'm going to turn on a tiny mu. And now you're going to see that the total energy, the gold graph, still stays constant. But which one is getting bigger? What color? Red. That's heat. We're losing energy to heat. That we don't get back, unfortunately. So that leaves less energy for the height and for the kinetic. And so we don't go as high and we don't go as fast. In fact, what's my final speed going to be here eventually if I let this play out?
0.
All of my energy will get transformed into heat. Wasted heat. That's the law of conservation of energy. That's a concept. Let's try a question with it. It says this. Projectile is launched straight into the air. If it reaches a final height of 93 meters, what was its initial velocity? And it wants me to use energy to solve this. Now, we could solve this with kinematics. We could say Vf equals 0 at the top. A equals negative 9.8. D equals 93. And then we would say Vi equals question mark. But I want you to know we can also solve this with the law of conservation of energy, G. KE initial plus PE initial, KE final plus PE final. Plus heat, although does this question mention friction or heat at all? Then let's assume we're ignoring it. This is a half mv initial squared plus mgh initial. That equals a half mv final squared plus mgh final. Mr. Dueck, what, Jaden? You didn't tell me the mass. No, I didn't. Why didn't I? Jaden, is there an m in the first term? Is there an m in the second term? Is there an m in the third term? Is there an m in the fourth term? So you're saying there's an m in every term? What does that mean? Mass is canceled. Also, are any of these 0? Now, for kinetic energy to be 0, Paige, we're asking, is V ever 0? So we're launching an object straight up into the air. When is the speed 0? Hello, people. When is the speed 0? At the top, which is? Potential energy has an H for height in it. When is the height 0? So I end up with a half V initial squared equals GH final. By the way, I wrote what is its initial velocity. Really, it should be what is its initial speed because it's a scalar approach we're using here. Okay. Wow, how would I get the V by itself? I'm actually going to, instead of dividing by a half times by 2, I'm going to write it as VI squared equals 2 GH. How to get rid of a squared? So I'm going to get the square root of 2 times 9.8 times 93. It's going to be 20 times 93 roughly, so it's going to be roughly 180. Square root of 180, 13 point something, 14 point something? I don't know. I think a little less than 14, a little more than 13, or am I totally off? I'm off by an extra decimal. Sorry, let's try that again. It's not going to be 13 or 14. It's going to be way bigger than that. What'd you get? 40. Yeah, that sounds better. Sorry?
42.7.
42.7, round that off properly. Again, let me emphasize, it is true, Sarah, we could have solved this with kinematics. In fact, I probably wouldn't choose to solve this with work and energy unless the question specifically said, solve this with energy. But where the law of conservation of energy, by the way, I tend to abbreviate it as the C of E, really shines is when you notice that there is a change in height, a change in speed, and a curvy path. Or when heat is involved. When is there a change in height and a change in speed and a curvy path? Roller coasters. And now we can finally analyze roller coasters. So example 2 says a 350 kilogram roller coaster car is traveling at 22 meters per second. The car starts out at a height of 12 meters. How fast will it be going when it gets to ground level? Ignore friction. We're in a DULP. There's my roller coaster path. At the top we have a car. What's its initial speed? 22. What's its initial height? And then here at the bottom, we'd like to find the speed. You okay with that, Ira? Ira, in this question, is there a change in height? Yeah. Ira, in this question, is there a change in speed? Yeah. Is there a yucky curvy path? This is a job for conservation of energy. That's the checklist I go with. Okay? So what's the law of conservation of energy? It says this. K E initial plus P E initial equals K E final plus P E final plus heat. Oh no, it says ignore friction. So before I jump in, are any of these zeros? Kinetic energy initial, that's your initial speed. Is our initial speed 0? Potential energy initial, that's our initial height. Is our initial height 0? Kinetic energy final, that's our final speed. Is our final speed 0? Okay. In fact, you know what? I can even tell you there's a built-in error check. What must our final speed be bigger than? Because I know how roller coasters work. Got to be bigger than 22. If I get an answer less than 22, I've done something royally wrong here. Okay? Our final height, Linnea, is our final height 0? Linnea, what's our equation for kinetic energy? You have your blue formula sheet out, like I said, yeah? I hope. KE is what? So KE initial will be a half MV initial squared plus PE is, so initial will have an H initial, equals a half MV final squared. How many of you have been on a roller coaster before? Everyone has? Even you been? Yeah. Okay. When you got on the roller coaster, before you got on, did they make you stand on a scale? Did they carefully measure your mass? Did they make sure they paired up heavy people and light people? Did they make sure that everything was all smooth and balanced? Why not? What? Look at our equation. An empty car will make it through the roller coaster the same as a full car. Because even though I gave you the mass, and I did, I think it was 350 or something like that. Did I need to give you the mass while? No. Now, when do masses cancel? When there's an M in everything. Zach, you going to make it? Because those blinks are getting longer and longer. Taylor, he needs your help a little bit. Here. Pause for a second. Linnea, what are they asking us to find in this question? Okay. And by the way, I picked my words carefully. I did not this time say find the velocity. This is why I was so choked. I used the word velocity in the previous question. I will almost always say find the speed, And my hint is use a scalar approach for these. I'm trying to hint that way. So I'm trying to find V final. How would I get that by itself? I'm going to show you a great trick. What's right in front of the VI squared? What's right in front of the VF squared? I tend to clear fractions. And how do I do that? I put a 2 there. I have to put a 2 there and a 2 there. I multiply everything by 2. You do have to multiply the GH by 2 as well. Why do I do that, Sharon? Because it gives me a lovely half times 2 cancels, half times 2 cancels. In fact, what I end up with is VI squared plus 2GHI equals VF squared. Well, B, you got your read sheet? When I say go, I'd like you to read me that equation right there. Everybody who has your, I said green sheet, blue sheet, everyone has your formula sheet. Look at the third equation from the beginning of the year. Mobeen, read it to me. VF squared equals VI squared plus 2A. Is G actually an acceleration? Yes. D, H is in meters. At the beginning of the year, I derived that equation with you, I think, this year. The VS squared equals VI squared plus 2AD. But really, the best way to derive it, Mobeen, is it pops right out of conservation of energy. There it is. VS squared equals VI squared plus 2AD. In this case, we've customized it because we know that A is G, and we know that the distance is height. That's why I think I also told you that equation wasn't a vector one, it was a scalar one. That's why sometimes you had to add the negative at the end of your answer afterwards. You had to interpret your answer, because when you took the square root, your calculator assumed you wanted a positive answer. That's the way I phrased it. Really, no, that equation's a scalar equation. You have to then put the vectors back in at the end if you need them. All right. I know the answer is bigger than 22. Square root of VI, what was VI? 22 squared plus 2, 9.8, 12. How fast will be going at the bottom of the roller coaster? Sorry? Give it to me at 3 sig figs, please. 26.8? Round it off properly? Okay. When do I really use conservation of energy? G. There's a change in height if there's a change in speed. Now, I may still be able to solve that with kinematics. Oh, if there's a yucky, curvy path, there's no other way to handle this. You guys can turn the page. Mr. Dillek, what if the roller coaster, instead of looking like that, what if the roller coaster had looked like that? Doesn't matter. It's a scalar. The law of conservation of energy doesn't care about the path that you took to get there. It only cares about where were you at the initial, where are you at the final. In fact, while the roller coaster could have looked like this just fine. We could have had loops in there, and as long as we end up right there again, we're fine. Now, I'll go with, a fairly simple case of kind of a couple of bumps and like that, but it doesn't matter. Chang, what's number 3 want me to find? Heat energy. Reading this question, is there a change in height? Is there a change in speed? Yeah. Is there a yucky, curvy path? No. It looks like it's straight. Are they talking about heat? Yeah. This is a job for conservation of energy. That's why on the previous page I said, or if they're talking about heat. So, I have to modify my equation a little bit. It still starts out the same. KE initial, PE initial, KE final, plus PE final. But now, since they want us to include heat, we'll say plus heat. Chang, before we go any further, are any of these 0? Is there ever a situation where my kinetic energy is 0? That means I'm at rest. Or where my potential energy is 0? That means I'm on the ground. Yeah, Patrick?
VI is 0.
VI is 0 because dropped. So you're saying we can get rid of that? I agree.
The height of that.
So which term is that? So if I'm hearing you correct, Patrick, you're telling me actually it ends up being PEI equals KEF plus heat? What we're really saying, Zach, is this. Here's the amount of energy you started with. At the end, most of your energy went into causing this object to speed up, but I guess you lost some to heat. What I really mean by heat is you bumped into air molecules, giving them motion. And you might recall from your grade 8, from your science 8 kinetic molecular theory, that moving particles have more heat. So I'm lumping it all into there. Let's get the heat by itself. I'll do heat in red. And then it's going to be PE final minus KE final. PE initial, thank you. Heat is going to be... Chang, what's the equation for potential energy? I know you were away, but I think you got it. Potential energy. It's on your sheet. Okay. So this will be mgh initial minus... What's the equation for kinetic energy? So, final. Chang, is there an m in this term? Is there an m in this term? Is there an m in heat? No. So masses don't cancel. I fibbed a tiny bit here. Really, the masses don't completely cancel. But if you grease the roller coaster down really good so that you don't lose very much to friction, the masses become negligible. You still have to take them into account, but barely. You don't have to put people on a scale. All right, here we go. M, 18, 9.8, 40, minus 0.5, 18, 25 squared. How much heat energy was generated here? 1,431. I'll go 3 sig figs. 1430 joules. Is that right, folks? No? Yes?
Yeah.
Yeah? Okay. So the law of conservation of energy says energy doesn't go anywhere. Energy doesn't come from anywhere. The amount of energy that you have. Well, really, it says this. If you have energy, it's got to come from somewhere. This is my go-to whenever people ask me science-y questions. We're going to pause for a second here. Example 4. Gurjot, what's example 4 asking me to find? Work. No, sorry. Stop. I thought you said the first. Read the first 3 words. Try that again. What? Work. Okay. What's that got to do with the law of conservation of energy? We'll get there. Taylor, work is what times what? Gurjot, in this question, do you see a force in newtons or a distance in meters? Anyway, this is, by the way, one of the many reasons I told you it's worth memorizing units. It cuts down on your thinking. I glanced at this. There's no force. There's no distance. And there's nothing easy to find. Okay. Work was also the area underneath a force versus distance graph. This is meant to be Captain Obvious. Do you see a graph? No. Okay. So what's our third definition of work? The work energy theorem. Read that to me, please, kiddo. Okay. Is this question suggesting or give any hint that we're on a hill? In other words, Gurjot, is this question suggesting there's any change in height anywhere? Okay, so is there any change in potential energy? What's changed in anything? So the amount of work to slow down this vehicle is going to be a half m v final squared minus a half m v initial squared. Final minus initial, it's kinetic energy, so it'll be a half m v squared. Gurjot, is there an m in this term? Is there an m in this term? Is there an m in there, Captain Obvious? No. Do the masses cancel here? Now, ready? Does it take more work to stop a semi-truck than to stop a little Austin Mini? Yes! Okay, so that makes sense to me. The mass should not cancel here. It's way tougher to stop a semi-truck. Okay. Let's plug and chug. Work equals 0.5, 1200. What's V final? 50 what? Oh, wait a minute. Who remembers from Physics 11, there was somebody with a 3.6. Was it? It was divide? Okay. Now, I will not on a test ask you to remember that. I would give you the conversion factor, but this was just to jog our memory. And Patrick, I'm lazy. I'm actually going to go 50 over 3.6 squared. Why do it on a separate line when I can do it all at once and not have to worry about rounding off at all? Minus 0.5, 1200, 80 over 3.6 squared. Am I going to get a positive or a negative answer? Ready? I'm going to ask you the same question. I'm just going to phrase it differently. Does the car need to gain or lose energy? Now, of course I'm going to get a negative answer. The car's got to lose energy. What do you get? You can get a fairly big number. What do you get? I think it's something in the 100,000s. Negative, yes.
180,560.
So 181,000 if I round off properly to 3 sig figs. Anybody else? No, yes? You didn't get that? Yes? Works better if we participate. So this question, Gurjot, sort of had 3 parts. Part A said, how much work? Part B asks, okay, what force does the work? Folks, what force does the work? Yeah. Now, if it's snowing, what happens to your coefficient of friction? What happens to mu? Smaller. So what happens to the maximum force of friction that your brakes can put out? It gets way smaller. Taylor, force is what times what? Sorry, work is what times what? So if your force gets smaller, but you still got the same amount of work, your distance, your stopping distance has to get bigger. And this is, again, my message as winter is approaching. I'm saying to you, Sarah, slow down when it's snowing. Nothing to do with your driving skill. The physics demands it. So where do you think this energy is transferred to? Heats up your brakes. But that's changing. Anybody here drive an electric vehicle or a hybrid? Or like parents own one? Nobody here has a Prius? Or wow, my last class, everyone. So not only do you not ride bikes properly, you're not environmentally... Okay.
They're expensive. Nobody rides a bike and zigzag up a hill.
Yeah, they do.
I've never done that in
Crazy
my life.
people, maybe.
I've never seen anyone else do that either. They go straight, even if it sucks.
You know what the problem is? Because you guys don't have any big hills. You'd figure it out in a big hurry if you had a steep, long hill and you didn't want to walk up it. You zigzag up it. Back to my point. Electric vehicles, which aren't as expensive as you think, they don't use the brakes to stop. They actually have what's called a regenerative braking system. When you take your foot off of the gas, rather than having to hit the brakes, they have a clever circuit that bleeds this energy, that 181,000 joules in this case, back into recharging the battery. And the car is losing energy, so the car must slow down. That's just the law of physics. You're losing energy, you must slow down. But it's not actually doing it with the force of friction. It's bleeding the energy off. This is why you've seen all the taxi cabs, almost all Priuses now, because you get much better gas mileage the more you hit the brakes. So if you're doing city driving, which is what taxi cabs typically do, you get great gas mileage because you're recharging your battery every time you hit the brakes. I took a Tesla for a test drive a couple of summers ago. And one of the things that the salesperson said is to slow down, you don't hit the brakes, you just take your foot off the go pedal. They don't call it a gas pedal because we don't use gas. So he was quite insistent, we're going to call it a go pedal. I said, I'll go with that. I'll go with, okay. Anyways, as soon as you took your foot off of the go pedal, it felt like the same feeling as you were hitting the brakes. But you weren't. Instead, the energy was being bled from the car and recharging the batteries. You only hit the brakes once you were almost at a complete stop. Then you had to hit the brakes to bring yourself to a complete stop. I said to the salesperson, I notice I'm hardly ever hitting the brakes. He said, yeah, we tell people get your brakes checked every 10 years or so. Because you're not going to use them very much. It's kind of neat. So we are getting better. One of the many reasons that electric vehicles are so much more efficient is every time you stop, you can recharge the battery. It's a fairly simple circuit. We'll actually look at the physics of it end of May, beginning of June. When we look at electric motors. We look at vacuum EMF. Example 5. A 12.5 kilogram object is pushed across a level floor with a mu of 0.35. Oh, I see friction. For a distance of 6.4 meters by an applied force of 58 newtons. Gotcha. Sharon, what's part A want me to find? Work. Taylor, work is what times what? Sharon, did they give me a force and did they give me a distance? Hey, I'm going to use that. In fact, my first thing I'm going to write here, I think, is work equals force times distance, but I'm even going to go F applied times distance because it wants the work done by the applied force. What was the applied force, Sharon? What's the distance? And I did a quick check. It says level floor. I think the force and the distance are in the same direction. So give this one to me. I think this actually ends up being a 4 sig fig. Give me the whole schmear. It's 700 and something, isn't it? Or 300 and something. 371.2. So let's suppose the applied force came from me. My body lost 371.2 joules because the energy's got to come from somewhere. But not all of it went into pushing this object. Not all of it went into making this object speed up. Because, Kieran, what's B want me to find? I think the work done by friction is going to be the force of friction times distance. I'm pretty sure the distance, Kieran, is still going to be 6.4. What's the force of friction? You know what? This is a job for a free body diagram. What are the forces acting on this block, Kieran? Get the obvious one. Gravity, you say? Are we sinking into the ground? Are we applying a normal force, you say? We have this applied force this way. And which way would friction be pointing? Okay. What's our equation for friction? Friction is what times what? Mu times the normal force. So the work done by friction is going to be mu times the normal force times d. I don't know the normal force, Kira, no, but look. Another force the same size as the normal force? mg. So it's going to be mu mg d. How much work is done by friction? 0.35, 12.5, 9.8, 6.4. What do you get? I think I'm going from memory. This one was in the 200s?
274.4.
274.4? And why must that be wrong? Because it's Patrick. No, why must that be wrong? Oh, because the force and the distance are in opposite directions, and this negative now means something a bit more, Jade. What we're saying is that's energy you lost in heating up the floor. Put the units, joules. So what's the net work done on the object? How much work actually went into making this object speed up? So we added 371.2 joules of energy, but we lost 274.4 joules of energy. What's left over to actually go into this object and turn into kinetic energy and make it speed up? 26.8. Ira, what's D asking me to find? Now, this would be an intimidating question if I gave you part D without walking you through part A or B or C. But letting you know we can. How am I going to do final speed? Well, it seems to me work is also the change in potential plus the change in kinetic. And Ira, I think the question did say level ground, did it not? So we can do that. And we actually know how much work. The work done was 96.8. What's changing anything, Ira? So this is going to be a half m v final squared minus a half m v initial squared. Although it said assuming the object started from what, Ira? So I can get rid of initial. And I can get the v final by itself. How? I think divide by m. I think times by 2. Square root. I think v final is going to be 2 times 96.8 divided by 12.5 square root. $3.94. I said to you, Ira, this would be a really intimidating question if I had just given you Part D. Actually, it wouldn't be, because most of you would have solved Part D using kinematics. So in Part E, it says, calculate the final velocity. Here's what you would have done. You would have said, right? What's VI? What's D? You would have probably then said, oh, I need A. How could you find A? Winner minus loser from my free body diagram. F applied minus friction equals MA. How would you get the A by itself divided by M? And then you can use VF squared equals VI squared plus 2AD. That's probably how most of you would do it, but I'm letting you know for what it's worth, the work method works. No pun intended as well. Okay? I'm not going to bother doing E because you're getting a little squirrely. I see people's head nodding. Turn the page. We're going to finish with this, a couple little thought experiments. We're going to go to the moon. Why to the moon? So that we can ignore air resistance. There's still gravity on the moon. It's a bit smaller than the Earth, but the physics will still hold. So it says this. 3 projectiles, A, B, and C, are fired from the same machine on the moon, no air resistance, with the same VI. Their paths are labeled A, B, and C. At the 3 points marked 1, right there, and right there, which projectile will have the greatest kinetic energy, A, B, C, or all the same? And convince me. Zach, you think it's C? So all 3 have same initial energy. In fact, what's their initial energy? A half mv initial squared, because their initial potential is on the ground. C has smaller potential energy, so larger kinetic energy. This is like that energy skate graph that we saw. The skate park, the skater. As soon as they go higher and higher, their potential got bigger, their kinetic got lower. So whichever one is lower has more kinetic energy, because the energy's got to go somewhere. I guess we should circle the right answer. C. All right. The next question. At each of these points marked 1, which one will have the biggest total energy? A, B, C, or all equal? Jaden. Law of conservation of energy. Energy is not created or destroyed. They all started with the same amount of energy because it does say that they were identical masses and they got the same identical velocity, which means their initial energy was a half mv squared. Their angles were different. Who cares? We're in Scalarville. At the 3 parts, at the 3 locations marked 2, which ones will have the biggest total energy at that point in time? And let's assume this is like a millisecond before they hit the ground, so they haven't come to a stop yet. They're right at impact. Tato. What were you going to say? Yeah, they do. It is all the same. Why? Did they all start with the same energy? Stop. Did they all start with the same energy? Energy can't be created or destroyed. They have the same total energy at anywhere in their path. No air resistance to bleed any heat away anyways. They have the same total energy at any location in their path. It just may be that at different locations, more of it is kinetic and potential for projectile A than projectile B or what. I don't care, but energy is not created or destroyed. If you want to get a head start on the homework, though, you can certainly already try number 1. We're going to continue this lesson next class. You're not going to hand this in next class. But you can try number 1. Number 1, where it says ME, that's mechanical energy. All mechanical energy is adding up potential and kinetic. I'm going to give you a hint. ME should end up being the same answer no matter where you are, because energy is not created or destroyed. It's just transformed. So you do number 1. You can do number 2, roller coasters. You can do number 3 and number 4. We'll pause there for now.